Intermediate Algebra. I'm Jim Helmer, and we're going to finish up section 6.1 in this video. This is video 2, dealing with roots and radicals. One thing we have to recall is our rules of exponents. If you don't remember all of your rules of exponents, feel free to go back to sections 4.1 and 4.2 and review your properties of exponents, your rules of exponents. But two of them we're going to look at is our product rule for exponents, because we're going to apply these to radicals, or similar rules to radicals. We have a to the m times a to the n. Our rules of exponents say if they have the same base, we can add their exponents. We can actually do some math here if they have the same base. Same thing with our quotient rule. If our values have the same base, we can do some operation to their powers, and in this case the top minus the bottom. This is our quotient rule for exponents. Well, we're going to look at two rules that deal with roots and radicals that are along the same lines as this. With our exponents, they have to have the same base. Well, similarly with our radicals, our product rule of radicals, they must have the same index. Now, if we look at this example here, we have the square root of a, so our index is 2, times the square root of b, so our index again is 2. If they have the same index, we can actually do this operation, the square root of a times b. Since they have the same index, we can multiply them under that index, that square root in this case. Same thing with the quotient rule. If we have the nth root of some fraction, we can actually split it up as long as they continue to have that same index. So I can say the nth root of a divided by the nth root of b, so we can split it up, or vice versa if we want to work backwards. Maybe I have a fraction that contains radicals. Well, if they have the same index, or I can do some operation to them so that they have the same index, I can then write it like this and maybe simplify a over b to some number that I can work with. If we look at this example here, we're asked to simplify the square root of 27. Well, I recognize 27 as a perfect cube, but this is asking me to say, what are its squares? The square root of 27. Well, if I factor it down, it's 3 times 3 times 3. Well, in this case, let me just grab a marker here. In this case, this is 3 to the third power. So I'm asking, what's the square root of 3 to the third power? Well, let's use this rule right here, our product rule, and break it up. This is how we simplify a radical. Well, I can say, well, this is the same as the square root of 3 squared times the square root of 3. So essentially I took this as a product and I broke it up into two separate radicals with the same index. They're still square roots. But what can I do with this? The square root of 3 squared, if we recall in the last video, I can say, well, I'm taking the square root of something squared. It is that value 3. So this here, I'll just write it over here, is 3 times the square root of 3. This is our simplified radical. So the square root of 27 is 3 square root of 3 when we simplify it. We make this radicand, what's under the radical, as small and as simplified as possible. Any numbers that we can pull out, we do so 3 times this quantity. We can do the quotient rule on this one here. We have the square root of 8 over the square root of 2. Essentially, we're going to work this rule backwards. My index is the same. It's 2. So I can rewrite this as the square root of 8 over 2. Now, I can simplify that. 8 over 2 is 4, so we can have the square root of 4. Well, the square root of 4 is a perfect square. We know that answer is 2. The square root of 4 is 2. So we can simplify this using the quotient rule. Let's look at some examples for our product rule here. We have the cubed root of 16. Well, 16 we can recognize as 4 squared, but it's also 2 to the 4th power. So this is a perfect 4th power number. So let's just rewrite it. The cubed root of 2 to the 4th power. That's the same thing as 16. Using our product rule, I can split this up as the cubed root of 2 to the 3rd, a perfect cube, times the cubed root of 2. So they still have the same index. We can use the rule. Here we have the cubed root of something cubed, that 2, times the cubed root of 2. So we simplified this using the product rule. Now through time and practice, we'll be able to look at this and say, okay, I can pull out 3 factors of 2. That's essentially what it's saying. Let's pull out these perfect cubes that are in there. And if I do that, I would still have a factor of 2 remaining. So I'm able to pull out a 2, and a factor of 2 remains under that radical. So 2 cubed root of 2. A quick, easy way of looking at it, which we'll see in the next section when we deal with rational exponents, essentially fractions as exponents, same thing as radicals. We'll say, hey, 3 goes into 4 once, 1 factor comes out. With a remainder of 1, 1 factor remains. So that's kind of a shortcut to go from here to here. All right, let's look at this example here. We have the cubed root of 40y to the 10th. Well, one thing we can do is, what is 40? Let's break it down. Well, 40, we can say, is 8 times 5. And if we memorized or know our perfect cubes, just by factoring it down, this is a perfect cube. Now, y to the 10th, well, we want factors of 3. I can say, well, this is y to the 9th times y. Using our rules of exponents, I could add these exponents and get y to the 10th. So this is the same value. So let's just rewrite it. The cubed root, using our product rule, of 8 and y to the 9th, my perfect cubes, times the cubed root of 5 and y. So I just split it up using our product rule, and now I can say, well, the cubed root of 8 is 2, and the cubed root of y to the 9th, well, y cubed times y cubed is y to the 9th. So it is a perfect cube of y cubed. Another way to look at it is 3 goes into 9 3 times. Pull out 3 factors of y. Excuse me. Now this here, it essentially is as simplified as it gets, the cubed root of 5y. So we took this value here, we pulled out what perfect cubes we could to get this, and this is our remaining value. So we have 2y cubed times the cubed root of 5y. What's under the radical is as small as possible. And we'll review these rules at the end of this video. Now here we have the square root of 12, r to the 9th, s to the 12th. Well, let's look at it this way. 12 is 4 times 3, and I recognize 4 is a perfect square, so I can take the square root of that. R to the 9th, I can think of that as r to the 8th, which would be r squared times r squared, or excuse me, r to the 4th times r to the 4th, with a remainder of 1. And s, well, the square root of s squared is 12. So I'm going to skip a few steps here, and I'm just going to break it down. The square root of this factor of 4 is 2. The square root of r to the 9th, I'm going to use that little shortcut method. Well, 2 goes into 9 8 times, right? Or 4 times, excuse me. 2 times 4 would be 8. So we can pull out 4 factors of r with a remainder of 1. 2 goes into 12 6 times, s to the 6th, with no remainder. So let's review what we did here. The square root of 4 is 2. The square root of r to the 9th is r to the 4th, because 2 goes into 9 4 times, with a remainder of 1. And 2 goes into 12 evenly, so there would be no remainder. So what remains? Well, I can't take the square root of 3 because that's an irrational number. We're going to leave it in exact form. When we divide 2 into 9, I get a remainder of 1, so one of the r's must remain. And 2 went into the 12 evenly, no remainder, so there's no s under that radical. So when we simplify it, what is under the radical is as small as possible. 2r to the 4th, s to the 6th. Now, when you first see this, you're like, well, where is he pulling these numbers out of? Again, with time and practice, we'll be able to see this, but you have to practice. When it comes to math, the only way to learn is by doing. Let's look at some examples that deal with the quotient rule. Now here I just have a fraction under a radical, so I can use my quotient rule to split it up because they will still have the same index, the square root of 4 over the square root of 25. Now by doing that, I can look at this and say, okay, well the square root of 4 is a perfect square, right? And 25 is a perfect square of 5, so the square root of 25 would be 5. So this simplified using the quotient rule to 2/5, a nice rational number. Now here we have two radicals being divided. They have the same index, so I can rewrite this as the square root of the top over the bottom. Still have the index of 2, it's a square root. But now I can simplify this. What is 64 divided by 16? Well, it is 4, the square root of 4. And we recognize 4 is a perfect square. 2 times 2 is 4, so the square root of 4 is 2. So by using the quotient rule, we're able to write it under a single radical and then simplify it and then take it from there. All right, what if we have here? What if we have some math operations on the outside? Well, order of operations says work within the innermost grouping symbols, and we can treat radicals as grouping symbols. Here they both have the same index of 4, so I'm going to rewrite it as 7 times these radicals. The 4th root of 162 and 2 being divided. And now I can maybe simplify this just like I did up here in this example. 162 divided by 2 is 81. Now maybe you don't recognize it, maybe you do, but 81 is a perfect 4th power number. It's the perfect square of 9, but 9 is a perfect square of 3. So 81 is actually 3 to the 4th, while the 4th root of a perfect 4th power number is that value being raised to the 4th power. So this would be 7 times 3. The 4th root of 81 is 3. But now we can do this multiplication. 7 times 3 is 21. So we get the result. This big radical here, things weren't looking very nice. When we simplify it, we get a nice number like 21. So that's why we learned to simplify our radicals. Now, to sum up essentially this section here is a radical in simplest form. There are 4 things that we must always keep account of when we're simplifying radicals. First of all, we can have no negative or 0 exponents. Essentially what we mean by that is if you see a negative exponent, immediately take its reciprocal, right? Because that's what a negative exponent tells us. The 0 exponent, hopefully we remember our rules of exponents, anything to the 0 power is 1. So if you don't remember those, or you might have been a while since you've reviewed those, go back to section 4.1 and 4.2, review your rules of exponents. The radicand, what's under the radical, contains no factors raised to powers equal to or greater than the index. Well, if we see here, 5 is greater than our index of 3. So what's under here, the radicand, has a factor to a power greater than the index. So we have to simplify that. Let's go ahead and simplify that. Well, the easiest way to do this is say, how many times does 3 go into 5? Well, 3 goes into 5 1 time. So take out one factor of x. 3 goes into 5 1 time with a remainder of 2. Well, that tells you how many factors must remain. A remainder of 2. So we get x cubed root of x squared. So that's how we can simplify radicands. This value must be less than that when we're all done and simplified. Notice now we have 2 as the power of our radicand, and our index is 3. 2 is less than 3, so we've met this goal here. The next one is the index is as small as possible. Well, if we look at this, 8 and 6, they actually have a common factor. So what it means by the index is as small as possible is we have to simplify this. If we think about this way, and we'll see it in the next section when we deal with rational exponents, these actually have a common factor. So we can simplify this. 6 is less than 8, so it meets this rule, but 6 and 8 have a common factor. And that common factor is 2, so I can say this is the 4th root of x to the 3rd. Now this value is less than that, and my index, this value out here is as small as possible. These are actually equal values, and these numbers were larger than these numbers, so we can simplify that. In the next section, this will make much more sense. And then the last thing we have to be aware of or keep account of when we're simplifying radicals is the denominator contains no radicals and no fractions appear under the radical. Now that kind of goes back to our quotient rule here. Hey, we had a radical in the denominator. When we finally came to our answer, there was no radical in the denominator. Generally, we do not leave radicals in the denominator, and our process of doing that is called rationalizing the denominator. And that's something we'll see in the very next, or in 2 sections away, 6.3. When we get to that video. So don't worry too much about this one right now. We'll rationalize denominators in section 6.3. And in section 6.2, the very next video, we'll actually see how we can use our rules of exponents to simplify these, and hopefully this will make a little bit more sense. So this has been section 6.1, video 2. Thank you for watching.